a master student from University of Malaya, a beautiful country in Kuala Lumpur, Malaysia. And I will present my research about the standard Martin-Rodrigues in detecting multiple persistence change. So let's get started. So persistence change is the change in the D parameter, which is the difference parameter in a time series data. So the detection of persistence changes is crucial, especially in economic data, for example, inflationary data, for improving model specification and forecasting performance. In previous studies, there are few studies regarding the persistence change where the D takes an integer value, which means that if the data is just from stationary to non-stationary, but there is, for my knowledge, there is very little knowledge about the change in the fractional D parameter. So that will be our focus to bridge that gap. And then the method that is presented by Martins and Rodriguez only focuses on the single detection of persistence change. So we wanted to, so our goal here is to extend that set. Uh, our goal here is to extend that set um, method into detecting multiple persistent changes. So there, so our goal is as we detect the multiple persistent changes, the forecastability will be improved and the error will be lesser. And also, and because of that, the forecastability, performance, and model fitting will be better. So for for our method here, we will run a Monte Carlo simulation to show that our method here will successfully detect multiple persistence change in the time series data, and we will compare it um, with a method from Leaborn to show that ours is good in detecting the change in the D fractional parameter, and then um, we will apply this to the inflation rate data to show its applicability. So this is the literature review. Just said that for structural change, detection is important for better decision making and also for policymakers to make better decision making. Okay, so this is the methodology for the extended Martin-Rodriguez method. So for this research, we focus on if there is two persistence break, but for this method, we can use it for more than two breaks. But for now, we will focusing on if there is two persistence break. So if there is a persistence break in the time series data shown K1 and K2, this is the null and also the alternative hypothesis, where there is a tree subsample, which for the first subsample, it takes a D1 fractional difference parameter, and the second one it takes D2, and then the other one is D3, and for each subsample it is divided by the breakpoints K1 and also K2. So this is the algorithm for the extended Martin-Rodrigues. So firstly, from the whole data set, we will estimate the long memory parameter D using here. And then from that D, we will filter the data by using this integrated uh, difference difference here, shown here as T. And then we will create a new variable as T minus 1 star, shown in equation number 3. And then we will choose a value of estimated breakpoint K, which we will say that it will be the candidate for the breaking point. And the searching area for the breaking point is from 20% to 80%, which is shown here as omega lower and omega upper. And the paper from Martin Rodriguez is suggested to make the lower omega or the lower part of the searching data is zero point 0.2, which is 20% of the data. And then from the 20% to 80%, we will fit the forward regression shown here in equation number 4. And then after we fit, the regression, we will use the OLST statistic uh, for each of the potential breaking points in the searching area. So, for example, if you have 1,000 sample size, so from we will search from observation number 201 until 800, and then those 800 observation will be considered as the um, candidate for the breaking point. And then we will sequentially check for each t statistic, and to know which is the possible breaking point, we will see for the infimum of the t statistic that we have found. So next we will determine the presence of structural change. So if the test statistic is significant, we will say that the potential breaking point is considered as the breaking point. So there is persistence change happen. So from what I have mentioned is from the Martin-Rodrigues, but for us, our contribution is it's just a simple one. Is we extend it a bit. So if the conditions here are met, which is T minus K star, we will stop the search and we will conclude that there is no potential addition breaking points after the detected breaking point. So if it's not met, we will repeat it again, but this time rather than using the new 30%, we will still use the same constant lower search. So like I used the previous example, if the lower is 200 for the next search, we will still use 200 as our lower search. Okay. Right, so for the forecasting, so this forecasting will be used to show that after detecting the persistence change, there is improvement in the forecastability. So we use three different forecasting models. First is the usual Botts-Jenkins model, which is called the ARIMA model, shown here in equation number 7. But sorry, and also for the next is the ARFIMA model. The difference is actually the same model, but the difference is the D here takes the D in the ARFIMA model used a fractional value rather than the ARIMA model uses a non-zero integer. Sorry, it's not non-zero, an integer value. Uh, so the ARFIMA model is because if the D is fractional, we said that the time series has a long memory time series case. And lastly, for the RT-FEMA model, there is an additional parameter, which is lambda, and lambda is the tempered parameter. And for this model, it takes all kinds of D is considered as stationary. Compared to the RFEMA, the D for the stationary is less than 0.5. Okay, so this is the three models forecasting models that we used. So for the simulation, we use this is the condition for the data generating process. So we set a sample size of 1,500, and we set the breaking point to 500 and so 1,000. That is our fixed breaking point. And we'll repeat it for 1,000 times. And for each subsample, we set the D, the long memory parameters or the fractional differencing parameters as 0, 0.3, and also 0.49. And then we will compare it with a method from Liborn, which is the same for persistence change, but for the integer. So, and we will denote the method as LET. So for our method, we will say that it is good because it detected near the supposed breaking point, which is observation number 500. So you can see here in the histogram, the detected breaking point by the method is near observation number 500 compared to the Leybourne is not so great compared to ours. And also, this is for the second detection. Again, ours is considered good in detecting the supposedly breaking point and compared to the other method. And then from here, this is the empirical rejection frequency to show that uh, our method for all 1,000 data sets, almost all of them are considered as almost all of the breaking points detected is considered as breaking points. So the null is rejected. And then for we could say that here in 0.88, we could say that almost majoritarily they are detected near the supposedly actual breaking point as shown in the histogram. So this is for the for our method, we apply this into the Philippines inflation rate data set. So this is the results, we could say, the detected breaking point and also the estimated long memory parameter. And this is by using the LET, the Lebon, the breaking point is considered like very, very near here when compared to ours. So this is our um, detected breaking points. And then after we detect the breaking points for both using the both methods, we will fit the three forecasting models that I already mentioned. And from the three models, we use RFIMA because the errors are the least. And then after we will fit it two more times, which is for the subsample after the first detection and also the subsample after the second detection. So this is the parameters used for the RFIMA. And for the forecast methods is shown here. We could say that after the second detection, the persistence, the errors are the least. And it is said that the persistence change is the persistence detection is important for better forecastability. But between the methods, the errors are not too great, not too much of a difference. So, but this is because of the second detection is kind of near between those two observations. So, uh, maybe in future we will look into it. So that is all from me. So this is all the references. So thank you.